Well, I hope that you guys are enjoying a nice little break and that you're working a little bit, but that you're also enjoying some relaxation time with your friends and your family, staying safe and all of that. So I'll try to be fairly brief, but not race through it. I know my general gear is to go too fast, so I'm going to try to keep myself going a little slower. So the first problem that I gave you was a nice little implicit differentiation problem. The first part is really not particularly scary. The first two, in fact. The third is actually pretty challenging, though. So I started the question by just taking a little derivative. Now, remember, this would be 6x dx. But then when we get to this next little piece right here, we have to do a product rule because the derivative of the first, which is 1, times the second, plus the derivative of the second, which is y prime, times the first. And of course, the derivative of 2y squared is 4y prime. Don't forget that. Now, again, a lot of teachers will require you to say dy dx because those primes look awfully conveniently small. Sometimes we can kind of forget them and it looks like it's a y to the first. And of course, the derivative of 36 is 0. We actually did phase 1, but I really would like to get that y prime by itself. So of course, we want to move the 6x and the y to the other side and then divide. So because we would have a y prime in common on those. Now for part B, it was pretty simple because we just had to plug in those numbers. I didn't need to get y by itself or anything like that, but I got 4/7 when I went through the process, and I'm not going to do too much with that. But when it comes to actually taking the derivative of the derivative, that is a little harder because I've got a quotient rule here. So notice that I have a low. Here's my d high. It would be -6 minus y prime. Minus high, there's my original, d low, 1 plus 4y prime, square of what's below. Now, the reason I highlighted those y primes is we're referring to y prime, but we already know what that y prime is, so we can substitute y prime in each of those places. Now, I actually did do some work trying to make that look a little bit better, see if that actually was a nicer result in the long run. And to be honest, no matter what I did, it did not actually get any better. So I just kind of opted on staying where it was. Actually, the big thing I did is I multiplied top and bottom by x plus 4y, which should turn this into a cube and make some of these get better, but it did actually make some of the other pieces get worse. So for question number 2, it's a similar problem that we wanted to look at, and that was looking to see when we have horizontal slopes. Now, if we want horizontal slopes, that is exactly where the derivative is equal to 0. So we're going to start it off by taking a nice implicit derivative. So notice derivative of x cubed is 3x squared. I got 3y squared y prime. A little product rule, derivative of the first would be -6 y plus y prime times 6x. Now, I kept going a little bit. I moved things around so that I could factor a y prime out of the portions that had it. Notice that I moved the 6y and the 3x squared across because they did not have it. So I found out that y prime was this fraction right here, 6y minus 3x squared over that. And if I want it to be horizontal, the only way that a derivative can be 0 is if the numerator is 0. So I took this portion of the fraction and I set it equal to 0. Which of course would happen if we did just a little bit of arithmetic or algebra. We could find out that 6y minus 3x squared is 0, making y 1/2 x squared. Now that feels like we've done everything we needed to do, but we really haven't. We need to go back and plug that into the original equation. So going back to the original and replacing all the y's with 1/2 x cubed here and here, we end up with a fairly simple little equation. I know at first you look at that and go, oh my goodness, we got an x to the 6th. But if we do just a little teeny bit of cleanup, combination of like terms, notice these both have an x cubed in common. So I personally factored a 1/8 x cubed out, which is going to leave me with an answer at x equals 0 and an answer at the cube root of 16. Now, of course, the last little stage of that problem is to go ahead and plug that back in. We also know right here that y is a half of x squared. So if I took x and I squared it and cut it in half, or I took the cube root of 16, I square it and cut it in half. That kind of finishes off question number 2. Pretty difficult little question. Now, question number 3. We're kind of done with that little idea, and we're going to be working on to the derivative of an exponential. We've got a product rule going on. So keep in mind it is x times this, and you want to remember the derivative of e to the u is e to the u times u prime, or e to the u du. So when I did that, I called this one f and this one g. So of course, the derivative of the first would be 1 times the second, which would be e to the sine x. Oh, interesting. Actually, I chose to do this problem a little bit different than I had thought about doing it, actually. I guess I decided I would take the log of both. So when I took the log of both using logarithmic differentiation, that's kind of funny. I didn't look over my solution. That allows me to separate those out because the natural log of x is fine and the natural log of e to the sine x is just sine x. So using logarithmic differentiation, we could have done product rule, and that's fine. I think I did it in fact over here, but 1 over y prime. And so the only thing that we would have to do in this problem is multiply both sides by y, which is the original problem, and we have our solution. Now, if you actually were to use the distributive property on this, you would actually get this answer over here. You can see in red, I did the derivative of the first times the second plus the derivative of the second times the first. There is a chain rule at play though, because the derivative of e to the u is e to the u times u prime. I think this particular case, the product rule was far faster than doing logarithmic. Now for part B, that's a little bit easier because the derivative of a tangent is just a secant squared, but don't forget, it's not only 3 times secant squared, we still have to take the derivative of the 5x portion, which of course is just 5. A fairly simple problem because all we had left to do is multiply the 3 and the 5 together. So that's going to be the first 3 problems on the review. Hopefully that worked out okay for you. I'm just going to go ahead and break it in very small chunks. All right, see ya. Bye.